All right, hey everyone. Good morning to you all. Today we will do anisotropy, and then we will talk about some of the basics of moment tensors. Mohit, can I please have share screen ability?
Yes, it's done.
Got it, thank you. All right, so anisotropy will more or less be the same as section 3.6 in the Sign and Wise session book that I've posted, although we are going to cover some things in a little more detail. So anisotropy is the directional dependence of elastic parameters. So C, our elasticity tensor, has 81 components. That's 3 to the 4th components. And up to 21 can be independent. Excuse me. Up to 21 can be independent. Now, in our past explorations, we've assumed isotropy, which means no directional dependence of elastic parameters. And then all we needed was 2 independent parameters, lambda and mu. In the presence of anisotropy, and we'll talk about this more, a shear wave will be split into 2 orthogonally polarized, separately traveling waves. And this is called shear wave splitting. And it's actually quite useful because it tells us something about the alignment of olivine in the anisotropic medium. And we'll talk about that more. So there are 2 dominant causes of anisotropy. One is shape preferred orientation, or SPO, and it's caused by inhomogeneous distribution of materials within the Earth. This figure on the right shows, excuse me, sorry, this figure on the right shows these long sort of lenticular features that cause seismic waves to travel faster in a horizontal direction than they do in a vertical direction. So a wave moving from right to left will see a different velocity than a wave moving from down to up or up to down. Another cause of anisotropy is lattice preferred orientation. And this occurs when the Earth is innately anisotropic on a mineral level scale. So if you look at this corrugated steel roofing, you can imagine if I had 2 plates, it's easier to slide the plates in the direction of the corrugations than against the direction of the corrugations. And olivine is somewhat similar. It's easier to deform it in one direction than in another direction. So what happens is the olivine A-axes tend to align in the direction of maximum shear. To describe anisotropy, a useful tool is the Voigt matrix. So recall our elasticity tensor has 81 components, 21 are independent. And what we do is we portray the elasticity tensor as a 6x6 Voigt matrix. And we can go from elasticity tensor to Voigt matrix by going, taking ij, so C sub 1, 1, that becomes C sub 1, where M is 1. KL, if that is 1, 1, that is 1. So C1, 1, 1, 1 would become C1, 1. C1, 1, 2, 2 would become C1, comma 2. So I'm just following these rules up here. The isotropic void matrix is given here. So here we see the CIJKL determination of isotropy, and below here we see the isotropic void matrix. You'll note that it's a symmetric matrix, and that symmetric matrix has all 21 components in it that can be independent. We can calculate strain given the stress. So similar to our sigma ij CIJKL, sigma ij equals CIJKL times EKL. And what we will use is the sigma from 1 to 6, which represents these terms on the left here of our standard 3x3 tensor. And then for the strain, we will use these terms on the right. And they represent these terms on the left from our 3x3 strain tensor. So what's notable is E4, E5, and E6 are actually 2 times E23, 2 times E13, and 2 times E12. So that is one perhaps surprising difference when we go and calculate the strain or stress with the void matrix. We can calculate transverse anisotropy, or transverse isotropy, sorry. That basically means that velocities horizontally traveling see one velocity, and then velocities vertically traveling see another velocity. And this is perhaps one of the simplest anisotropic situations. And the void matrix for that is given up here. And you can see there are a few parameters, A, N, F, and L, and C. So these 5 parameters explain the simplest case of anisotropy or transverse isotropy. In the x1, x2 direction, so this is x1 and x2 is in and out of the screen here. VP1 equals square root of A over rho, VS1 equals square root of N over rho, and VS2 equals square root of L over rho. And again, we're seeing shear wave splitting here. So shear waves will split into 2 orthogonally polarized or nearly orthogonally polarized separately traveling waves. In the x3 direction, so going vertically, we see VS1 equals VS2, and those both equal the square root of N over rho. So if I'm traveling horizontally, I see the P wave traveling first, then S1, and then S2. If I'm traveling vertically, I see the P wave traveling first, and then S1 and S2 are superimposed on each other. This says S1 and S1, but it's actually S1 and S2. Transverse isotropy is often characterized by these parameters, eta, phi, and I forget what this term is called. Does anyone know what this Greek letter is called?
I think it's zeta.
Who's zeta?
Yeah, it is zeta. Zeta.
Okay, so this is zeta, phi, and eta. And typically for layered structures, zeta is greater than 1 and phi is less than 1. In an isotropic case, zeta, phi, and eta are all the same. So in this case, we have 3 independent parameters, which is 1 more than the isotropic case. So this is a simplest type of anisotropy. And I should say that even though it says transverse isotropy, that's just indicates that horizontally waves see the same elastic parameters, but vertically they don't. So it means only in the transverse direction things are isotropic. If the X3 axis is turned horizontally, we get azimuthal anisotropy, in which P wave velocity varies with azimuth. So it looks something like this. VP will vary with azimuth as A1 plus A2 cosine 2 theta plus A3 sine 2 theta plus A4 cosine 4 theta plus A5 sine 4 theta. In the lithosphere, the magnitude of the 4 theta component may be small. Studies have shown that, and it's often ignored in teleseismic studies. However, people will often calculate A2 and A3. So they will parameterize the P wave velocity as A1 plus A2 cosine 2 theta plus A3 sine 2 theta. In the case of cracks, we also get anisotropy. This is a case of shape-preferred orientation. And the anisotropy looks like this, where we have 1 minus eta term in C55 and C66. And eta equals n a cubed over v, where n is the number of cracks in the volume, v, and a is the half width of the cracks. If these are fluid-filled cracks, the P wave velocity is not affected, but S wave velocity is affected. So we have a further reduction in the shear wave velocity. Also, we can find in cases where there's melt will often form films, and these films can produce anisotropy as well. So some important terms for discussing anisotropy. So radial anisotropy, and that means there's a difference in propagation speed between horizontally and vertically polarized waves. So SH versus SV, or Love versus Rayleigh waves. Azimuthal anisotropy, which means that there's a directional dependence of wave speed with azimuth in the horizontal plane. Transverse isotropy, and this is equivalent to hexagonal anisotropy. It's a simplified description often of mantle anisotropy with 5 independent parameters. And we can have vertical, so this is vertical transverse isotropy, horizontal transverse isotropy, or tilted transverse isotropy. And then there's polarization anisotropy, which is anisotropy that manifests in the polarization behavior of waves. And we'll see this in a little bit. All right, so here's where I'm going to deviate from the book a little bit and show you how the Kelvin-Christoffel equation is derived. And I'm going to give you an example of calculating with it. So once we have this equation here, the eigenvalues of this equation tell you the velocity of the quasi-shear 1, the quasi-shear 2, and the P wave. And the eigenvectors give the polarization directors of these 3 waves. So the shear waves, because they split into 2 separate polarized components, we call them quasi-shear 1 and quasi-shear 2. So we're going to start with our relationship between stress and strain. And we are also going to add our definition of strain in terms of our deformation function. And I will note here that d sub L u of k is just du of k dx of L. This is just a shorthand way of writing a derivative in summation notation. So we can write out our stress-strain relationship. So here is our stress-strain relationship for sigma sub ij. And now we can substitute in the derivatives of u for E. So we're going to take these values here and substitute in E11, E22, and so on. That gives us this here. So here we are just basically writing out what stress is in terms of elasticity and deformation. Now, we will recall from the first lecture that the homogeneous equation is rho times the acceleration, so d squared u dt squared, and that equals d sub j sigma sub ij, again using the summation notation abbreviation. And now we can put our new formula for stress into this. So rather than sigma sub ij, we're going to add Cijkl and the partial derivative of u of k with respect to x of L. And we can write that like this here. Okay, so let's assume a plane wave solution to this. So our deformation function u is going to be a polarization vector times a sinusoidal wave. And that sinusoidal wave is traveling in a direction given by the slowness vector s. S equals 1 over c, where c is the phase velocity. And here I'm going to distinguish between phase velocity and group velocity because these are different in anisotropic systems. All right, so what we will do next is calculate the derivatives for this solution and see what useful relations come out. So the time derivative of u is going to be minus I omega times u, and the second time derivative is going to be minus omega squared times u. The spatial derivatives, dl of u of k is just du of k dx of L, and that's going to be minus I omega minus s of L times u of k. And the same thing for the second derivative. In this case, it's going to be minus omega squared minus s of j minus s of L times u of k. So we're going to plug these into the homogeneous equation. So we've just plugged in our terms. And here I've simplified in terms of summation notation. And I've removed common terms. And we can note that g of I equals g of k when g of I equals delta, the Kronecker delta ik times g of k. And so we get c sub ijkl, s of j, s of L minus rho delta. Again, this is the Kronecker delta ik, all times g of k. Okay, so we're getting close. So let's define two variables. One is we will take our elasticity tensor and normalize it by the density and call it capita gamma. And then we will also look at the length normalized slowness vector. So it's our slowness vector divided by the velocity. So this has a unit length. With these variables, the equation becomes capital gamma ijkl s hat of j times s hat of L all over c squared, well, here's the phase velocity, minus delta ik, our Kronecker delta, times g of k. Or we can multiply through by c squared and get this here. And now we will define m sub ik as gamma ijkl, s of j, s of L. And here I'd note we have two dummy or summation indices, so s of L and gamma sub L, and s of j and gamma sub j. So we are only going to have 6 components, or well, 9 components to mik, and the j and L will be completely summed over. So what's notable is that m will be different for each plane wave direction. So we will consider a plane wave in an isotropic medium hitting this anisotropic medium, and the plane wave will have direction given by the slowness vector. So our final equation is m sub ik minus c squared delta ik times g of k. And this is an eigenvector eigenvalue equation with 3 solutions. The 3 eigenvalues give the phase velocity squared for 2 quasi-shear waves, so QS1 and QS2, and 1 quasi-P wave, QP. The eigenvectors give the polarizations of the quasi-shear wave and the quasi-P waves. Note that if M is not a symmetric matrix, the QS1 and QS2 are not necessarily orthogonal. However, typically when we have our wave imposing at a crystalline symmetry axis, our quasi-shear waves will be orthogonal. In the case of isotropy, there are still 3 eigenvectors, one for SV, one for SH, and one for P. And the SV and SH waves, which are orthogonal, will have the same values for C, or the same phase velocities. All right, so that's kind of complicated. And now let's do an example, and hopefully this will help you understand it a little better. So we will take a Voigt matrix for olivine, and then we will convert it to gamma. So I'll divide through by density. And notice that this is in gigapascals, and I've converted to pascals. So I'm 1 times 10 to the 7th times these units here. And the units of pascals are kilograms per meter second squared. So when I multiply that out here, I get units of gamma as meter squared second over second squared, which makes sense because the eigenvalues are the square of the velocity. Okay, so let's assume a ray is propagating with normalized slowness 1 over radical 2, 1, 0, 1. So it's propagating in the x direction and the z direction at basically at a 45-degree angle. Now first, let's calculate m sub ik. So m sub ik is gamma sub ijkl times s of j and s of l. So we will loop through I equals 1 to 3 and k equals 1 to 3, because these are the free indices, and we will calculate, as an example, I equals 1 and k equals 1. So m sub 1 is going to be the summation of j equals 1 to 3 and the summation of l equals 1 to 3, gamma 1 comma j comma 1 comma l, s of j, s of l. And now we have 9 terms here. So we will write out all 9 terms. So that equals gamma 1, 1, 1, 1, s of 1, s of 1, and so on. All right, so s of 1 is 1 over square root of 2, s of 2 is 0, and s of 3 or s sub 3 is 1 over square root of 2. And so we can plug in these values for s sub 1, s sub 2, and s sub 3 to get m sub 1 equals to this. And then we can convert the gamma matrix to Voigt notation. So gamma 1, 1, 1, 1 is just gamma 1, 1. Gamma 1, 1, 1, 3 is gamma sub 1, 5. Gamma 1, 3, 1, 1 is gamma sub 5, 1, and so on. And then we can go back to our gamma Voigt matrix and plug in these numbers. And we get m sub 1 equals 5.9366 times 10 to the 7th meters squared per second squared. Now you would do this with each of the 9 components in the M matrix. For instance, we can do m sub 1, 2. And here I notice this one's a little trickier to convert to Voigt notation because we have gamma 1121 right here. And there isn't a 2-1 into something option for Voigt notation. So what we do is we take into account the symmetry that gamma sub I JKL equals gamma sub I JLK. So we can note that gamma sub 1121 is equal to gamma sub 1112. And for this, the Voigt notation is given, and it's 1,6. So we calculate all these terms and put them into Voigt notation. And then we find that gamma sub 1,6, gamma sub 1,4, gamma sub 5,6, and gamma sub 5,4 are all zeros. So m sub 1, 2 is going to be 0. And you will actually find this fairly often. All right, so the phase and group velocities are often in different direction when there's anisotropy. So the group velocity direction, so as a function of coordinate system, is going to be gamma sub I JKL G of J, so the polarization in the J direction, S of K times G of L. And we can also take into account that U of I, S sub I equals 1. So what this means is if I plot the wavefront created when I've had a source at the origin here, the wavefront will move out with the group velocity. And in a particular point, the group velocity will be moving in this sort of angle direction, yet the phase velocity is perpendicular to the group velocity surface, and that will be straight up x3. We can also do the slowness surface, which is the inverse phase velocity. And in that case, the phase velocity moves straight up the S3, and then the group velocity moves at an angle to S3. So the point here is just that the group velocity and the phase velocity do not move in the same direction. We can plot the vertical slowness and the vertical group velocity of olivine. And this is olivine with A-axis horizontal, which is pretty common in the upper mantle. And then B and C axes randomly rotated. So basically we just have an A axis that points horizontally, and then the B and C axes that are randomly oriented perpendicular to this. And we can see quasi P, quasi S1, and quasi S2. And from this, you can calculate the phase velocity and group velocity. So finally, I'd like to note that the particle motion, which is G, so that's the polarization direction, that is also going to be varying between the group velocity and the phase velocity. So there's a lot of richness to anisotropic structure. All right, so anisotropy in the crust is due to things like faults, cracks, myelinite zones, migmatites, gabbroic intrusions, all sorts of cumulates, anything that orients in one direction and not in another direction. Anisotropy in the mantle is predominantly lattice preferred orientation, which is also called crystallographic preferred orientation. And it's most dominantly caused by alignment of olivine grains. And so olivine in the mantle will tend to align in the direction of a sinospheric flow or maximum lithospheric strain. And here's an example from a mid-ocean ridge where we looked at P-wave velocity as a function of angle. And you can see that P-wave velocity varies by about 0.3 to minus 0.3. And this is just due to alignment of olivine. A common way to measure anisotropy is through shear wave splitting. So we start with an SKS wave. So here's the source. It travels as an S wave, then as a P wave through the outer core. And then right here, the P to S conversion only produces SV energy. So any SH energy that was here has bounced off as an SCS. So right here, all we have is SV energy. And that is going to be in the direction between the receiver and the source. So your radial channel of your seismogram will only have the seismogram will only have radial energy. And so we can call that the source time function and say it's solely on the radial channel and not on the transverse channel. And if I plot the seismogram on a radial versus transverse channel, it'll just be shaking on the radial channel. After encountering an anisotropic layer, the wave gets split onto the fast and slow axes. And the fast axis is generally the alignment direction of your olivine A axis. And what happens is your shear wave gets split into two nearly orthogonally polarized waves, and the blue wave travels faster than the red wave. So the blue wave is called the fast wave, and the red wave is called the slow wave. And when I project the radial energy into the anisotropic reference frame, I have energy that shows up on the fast axis and the slow axis. And the wave that occurs on the slow axis is delayed by a certain arrival time that we typically call dt. And typical values for dt from the upper mantle shear wave splitting are 0.5 to 3 seconds. Phi is the angle between the initial polarization and the fast axis. So the fast axis can be an arbitrary orientation, and our goal is to measure it. So at the seismometer, we typically look at the wave in the RT coordinate system. So the radial is the SB and the tangential is the SH. And to understand the waveform we see, we want to rotate the fast and slow waveforms into the radial and transverse channels. So our wave has been split into a fast traveling wave and a slow traveling wave. The fast wave is offset by a value dt, a time offset from the slow wave. And now what we observe on our seismometer is the radial and transverse channels. So we have to take the fast wave and project it onto the radial and transverse channel, and then add in the slow wave. And here is this done. This is just trigonometry. So the radial channel has the source time function of the original earthquake times cosine squared of phi, where phi is the fast axis angle orientation with respect to the radial channel, and then s of t minus dt sine squared phi. So this is the slow wave and this is the fast wave. And the transverse channel looks like this. So the fast wave originally starts out as s of t, and then it becomes S of t cosine phi as it gets projected on the radial channel. The slow wave becomes S of t minus dt times sine of phi. If d is the distance the waves travel in the anisotropic material, and v1 and v2 are the velocities of the quasi-shear 1 and the quasi-shear 2 waves, then dt equals the distance they travel through the anisotropic material over the fast wave velocity minus d over the slow wave velocity. Typically, we expect dt of roughly 1 second, and for a typical value of anisotropy, we generally consider v1 and v2, or v fast and v slow, to be offset by about 4% from each other. This would imply that a dt of 1 second corresponds to about 100 kilometers of wave propagating through anisotropic material. So here I've just drawn out what we see. So we have a source. This is an S wave with both SH and SV components. The particle motion in a plane perpendicular to the ray path will have both SH and SV energy. Then at the core mantle boundary, the SH will be reflected and the SV energy will convert to a P wave. And then the P wave will convert back to an SV, and I get an SV. And then when I hit the upper mantle, then I see anisotropy, and SV energy will actually end up on the SH channel as well. And we will measure that with our seismometer. So to measure shear wave splits, what we do is we rotate the observed radial transverse seismograms through successive test angles until the traces on the two channels are the same. So we start out with figure A here. We have an uncorrected SKS, and then we rotate it until the fast and slow waveforms look quite similar. And the reason we do this is because the fast and slow waveforms should both be reflected of S of t, which is your source time function from your earthquake. And you can see that the fast wave comes in a little bit quicker than the slow wave. So this is the travel time offset. This is dt. And then we can account for, we can shift these by dt so they both align up, and then rotate them back to the radial and transverse channels. And when we do that, we have all the energy on the radial channel and 0 on the transverse channel. So in a sense, we've corrected for anisotropy. And what we typically do is we rotate and we try different delays, and we see which rotation and delay best minimizes the transverse energy. And we get something like this, where the center here is where the transverse energy is minimized. Here is a plot of shear wave splits in the Western United States. So you can see there's interesting directions. And this is probably due to a sinospheric flow, at least in the West, where we have a thin lithosphere. In the eastern part here, we probably also have lithospheric fabric. And this lithospheric fabric could have been developed 1 billion years ago. We don't really know. So yeah, this is the shear wave splitting for the United States. We can also look at zeta, and zeta is SV over, SH over SV. And so where SH is greater than SV, then I see higher values of zeta. Where I see negative values of zeta, SV is greater than SH. And we can measure this by looking at the relative arrival times of Lev waves and Rayleigh waves as a function of wave frequency. So you'll recall that Rayleigh waves and Lev waves both are sensitive to deeper and deeper structure when you go to longer and longer wave periods. So if I look at SH, or my Lev wave velocity, and my Rayleigh wave velocity as a function of wave period, we can derive these plots like this. And what we think is happening is the mantle is generally convecting up and down below 200 kilometers, and then above 200 kilometers, it's generally convecting horizontally. All right, any questions on that? I know the Kelvin-Christoffel matrix is a little bit complicated.
No questions?
Yeah.
One thing, how did you get the void matrix values? Did you measure them in the lab?
Yeah, typically they would be measured in the lab.
Okay, so you just take, how do you get the course? So you get the core in 90-degree angle and then 45, and then, I mean, what type of measurements are they that give you so many different measurements?
So what they do in the lab is they calculate the velocity it travels in every direction, and then they solve for an elasticity tensor that best fits those velocities.
Okay, so the cores are oriented in 90, 45, and all types of angles, right? Not just 3 angles, right? Okay.
Yeah.
Okay. Then in the group versus phase velocity diagram,
Yeah,
if there's no anisotropy, then both of the velocities would be the same, right?
that's correct, yes.
Do you see that in the seismogram, like the group and phase velocities? Can you identify those peaks on the seismogram?
No, I don't really know how to do that. I imagine someone has come up with a clever way to do that, but I've never seen it done personally.
Okay. Okay. Another question is, when you say M11 is 5.39 or M12 is 0, what is the exact meaning of M? You know, that in that matrix when you calculate?
So M is a matrix that gives the velocities for a given wave slowness. So it's the, I don't know if it has a distinct meaning other than it, the eigenvalues and eigenvectors tell you the polarization and the velocity of your 3 waves. I think what's important to note is that your M matrix will vary for each slowness direction. So if your wave hits your anisotropic medium in a different direction, you have to calculate a different M matrix.
Okay, so it's some type of modulus converted into some other form of modulus, right? So I see.
And there are codes out there, like there's one called, I think, MSAT, that's MATLAB code that will calculate your M matrix and for any arbitrary direction.
Okay. Okay. One thing about the conversion of that wave from S to P and then to SV, why is that happening? Like one part of SV is lost at that boundary, and then it goes to P, and then when it comes out, then it I mean it just has the SV and not the SH. Is there an explanation, or is this just an observation?
Yes, so the reason is when it hits the liquid core boundary, only the energy that's aligned such that it can make a P wave can actually be transmitted. And then that turns out to be only SV energy. So the SH energy is all reflected, and that becomes an SCS wave. So then your P wave, when it leaves the outer core and then travels back through the mantle, it's only aligned in such a way that it can make an SV wave. And therefore it makes an SV wave, and there's no SH energy until you encounter anisotropy.
By alignment, you mean the angle of incidence?
And the polarization direction as well.
Okay, okay. Okay, one last question is that you said that Rayleigh and Love waves only travel at this, those are surface waves, right? But
Yes.
you also show them that they can be observed that their velocity was something at 200 kilometers or 100 kilometers depth. But if they are only traveling in the surface near the Earth's surface, then how do you measure it so deep, 200 and 100 kilometers? Am I interpreting it correctly, or is it something else? That last diagram you showed us.
So a long period surface wave, say a 100-second wave period surface wave, is actually sensitive to structures between 0 and 200 kilometers in the near surface. So these long period surface waves are sensitive to fairly deep structure. A say 20-second surface wave would only be sensitive to structure in the top 30 kilometers or so.
Yeah, that's fine. But why do we call it surface wave then, if they are just sensitive to so deep like structures? Because
they follow the surface, so they don't dive down like body waves do. They actually follow the surface, and they vibrate all, say, 200 kilometers of the outer part of the Earth.
Okay, okay, thank you.
Mhm. Any other questions? All right. I will take a 5-minute break and get something to drink, and then I'll be back and we'll talk about the beginning of moment tensors. All right, I guess we can talk about moment tensors now. Okay, so I don't know if anyone's reading the Steinway session book, but earthquake seismology, which is today and tomorrow's lecture, are in chapter 4 in Steinway session. So we just finished up chapter 3, and we are going to briefly go over moment tensors. So we will cover the earthquake cycle, Green's functions in the moment tensor, earthquake faults and seismic moments, non-double couple sources, and radiation patterns and beach balls. And that will be in today's lecture and also tomorrow's lecture. So first, I just want to show you some pictures to one, emphasize that earthquakes are a major hazard. So here's a fault scarp. This is a school that was destroyed by the 1964 Alaska earthquake, which was like a magnitude 9.2 earthquake. This is the 1906 San Francisco earthquake, which subsequently caused a fire, and the fire destroyed much of the city. And here's a fault in Pakistan. Here is vertical slip from the 2002 Denali earthquake up in Alaska. And here as well is slip from the earthquake. Of course, not all earthquakes produce fault scarps. Some earthquakes slip below the surface and they don't actually rupture the surface. Here are some examples of right lateral strike slip faulting. So this road here, or these farm rows here. And here's some right lateral motion from the Denali earthquake. You can see right here that the road was destroyed, but the Alaska pipeline, which was engineered to survive a great earthquake, did not break. So that is good. We can also look at river channels to indicate the sense of slip. So here's a river channel, and it's been offset to the right with respect to this part of the channel. And same thing here, we have a river channel going like this. This is slip on the 1906 San Francisco earthquake. This is one of the large ones that have affected the San Andreas fault. It's a fault that runs along the US West Coast, and it's probably one of the greatest sources of seismic hazard in the United States. And if you look at surface slip, it goes from 1 meter at San Juan Bautista to 3 to 4 meters past San Andreas Lake. So up here, we actually had more slip than down here. So earthquakes can be understood through elastic rebound theory. And this was actually invented before plate tectonics, but it actually provides a good framework for understanding stress and strain. So at first, at interseismic phase, the fault is locked, and you have far field motions that occur, but at the fault, no motion occurs, and you get all this stress that builds up. You have a pre-seismic phase, perhaps with foreshock or other precursory events, and then you have a co-seismic phase, which is shown by figure C here, where you have rapid slip on the fault. You have a post-seismic phase where you have aftershocks and transient after slip the viscous part of the lower crust may deform over a matter of years in response to the near surface rupture. And then you go back to the interseismic phase. So we are going to start talking about Green's functions, and you may recall the momentum equation. This time I'm going to add body forces, so F of I. And we've ignored them up until now, but we need to consider them since earthquakes are a body force. So one way to deal with forces is to start out with the simplest possible force, which is a delta function impulse. So this force will have a direction and a location. And the response of the Earth to this force at a location and time x of t is the Green's function. So u of x of t is the deformation function, and that's going to be the Green's function, which is going to be a function of both where you're measuring the deformation and where the force occurred, and it'll also be a function of the force that's occurred. So in summation notation, the displacement vector is going to be g sub ij times f of j, where g is the Green's function, and that basically summarizes all path effects, and then f is a body vector force. So it turns out that this is a linear system, so we can sum up the effects from different sources. So imagine I have f of a, which creates u of a, and f of b, which creates deformation u of b. We can just add the effects of f of a and f of b to get the total deformation. And in this case, it's u of a plus u of b. So with that in mind, now we need to figure out how to represent slip on a fault with equivalent forces. So in map view, first motion in the far field is going to be a combination of compression, dilatation or extension, compression, and dilatation. And the compression is indicated by up on your seismogram, and dilatation is going to be indicated by down on a seismogram. So to represent these far field motions with point forces, we need to use force couples. So the force couple needs to produce both the observed far field motions, so the compression and dilatation, but also it cannot produce a net torque. So this one here doesn't produce a net torque, but it would make all far field motion compressional. This field here produces the appropriate far field motions, but it has a net torque. So to properly mimic an earthquake, we need a double couple. So we need this green first couple, and then this blue dashed line, a second couple. And if we create these two couples of forces, that can mimic what happens on this fault, which has slip shown by these black arrows. So we should note that the far field displacements are non-unique. So I could have motion with the upper part moving to the right and the lower part moving to the left, or I could have this right part here moving upwards and this left part here moving downwards. So the plane perpendicular to the actual fault plane is called the auxiliary plane, but we can't actually infer which plane slipped from far field motions alone. So as a consequence, our double couples are the same both for the fault plane and the auxiliary plane. So we define M sub ij as a force couple with the opposing forces along the ith axis. So here's the ith axis. So this is m sub ij. And m sub ij has magnitude of force times the distance that the forces are separated. So it's a moment. So m sub ij is one component of the moment tensor. And this is different from the m sub ij that we just calculated with the Kelvin-Christoffel matrix. This is a completely different topic. So we can represent slip on a fault of arbitrary orientation as a series of these fault couples. So m sub 1, 1, m sub 1, 2, m sub 1, 3, and so on. So m sub, the second character indicates the offset of forces, and the first number indicates the direction of the forces. Because of conservation of angular momentum, each couple must be balanced. So m sub 1, 2 equals m sub 2, 1. So m sub 1, 2 and m sub 2, 1 have to be the same. And that just produces our double couple. All right. So for a point force, U sub I equals G sub ij times S sub j. G sub ij is our Green's function, and it translates what happens with a body force to deformation at an arbitrary location. Now the displacement at x due to a force couple can be written as this here. So this is G sub ij at x naught, t naught, and this is G sub ij at x naught minus x of k times d. So this is the difference in the force. So here's your original, here's your original force, and then here is your couple force, which is offset by x of k times d. And because it's in the opposite direction, we have a negative sign here. We can rewrite this, and it turns out that this is just a derivative as d goes to 0. So we can, as x of k goes to 0. So we rewrite this as this. And note that k is a repeated index. So this involves all the products f1 of d, f2 times d, f3 times d, which is just a whole bunch of possible fault couples separated by distance d. This here looks a lot like the moment tensor. So in math terms, m of jk equals our body force times xk times d, which means the displacement equation can be written as dgij dx naught times our moment tensor. So let's tie this all together with earthquake faults. If this is a right lateral earthquake, it will have this sort of double couple. And our moment tensor will be m sub 1, 2 and m sub 2, 1. And m sub 1, 2 and m sub 2, 1 will have to equal each other to prevent net rotation. So we can also introduce the scalar seismic moment, m sub naught, which just equals m sub 1, 2, which equals m sub 2, 1. So our moment tensor just equals these components with m naught in it. And m naught is the shear modulus or the rigidity of the Earth times the fault displacement times the fault area. So technically, the fault displacement varies with time, the fault area varies with time, and it varies in shape. But for now, we will assume that D is constant, A is a rectangle, and these both occur instantaneously. M naught has units of work, typically expressed as Newton meters, to express that it's a force acting over a distance and not the energy radiated out by the earthquake. And we won't forget that this double couple can either be due to fault slip on this direction or this direction. So it can be, one of these can be the fault plane, the other one is called the auxiliary plane. And from our far field motions measured by seismometers, we cannot figure that out. So to distinguish between the primary and auxiliary planes, more information is needed, such as the surface rupture, a distribution of aftershocks, or a known fault location. Since the moment tensor is symmetric, we can also find a set of axes that diagonalizes them, just like we can do with the stress and strain tensors. So in this case, we can intuit that a 45-degree rotation will do it. So we have our new moment tensor is equal to m naught and the m11 component and minus m naught and the m22 component. And an equivalent force couple is that with x1 going outwards and x2 prime going inwards. So here we've produced a different couple of forces that are equivalent to our double couple. We call the axis on the x2 prime, so the compressional force, the p-axis, and the tensional force, the t-axis. And for an arbitrary moment tensor, m naught is going to be 1 over square root of 2 times the square root of the sum of all the components of our moment tensor matrix. We can also define our moment tensor in terms of the vectors that define the fault system. So if d hat is the unit slip vector, so the direction that the fault slipped, and n hat is the unit vector normal to the fault plane, we can calculate m naught from these parameters. And as with all tensors, the moment tensor can be rotated using a transformation matrix. A useful rotation is one that orients the axis into the PT axis coordinate system. So we might have something like this, where T is defined as the normal plus the normal to the fault plane plus the displacement vector. P is defined as normal minus the displacement vector, and B is the normal cross the displacement vector. So this is your t-axis, and this is your p-axis, and this is how they actually relate to the fault that's actually slipped. And so if we have a moment tensor in terms of these parameters, we can calculate a alternative moment tensor that just has a positive and negative moment on 2 of the diagonal terms. And this is equivalent to rotating it into the PT axes. We can also have non-double coupled moment tensors. So an explosion would produce a triple vector dipole with a non-zero trace 3e. So here's a typical moment tensor from an explosion. An implosion would be the same thing, but with negative values. Mine collapses, bombs, meteorite impacts would all produce non-double couple moment tensors. And that's all I had to say about moment tensors. I will finish them up on tomorrow. Does anyone have any questions on moment tensors?
Sir, are there any limitations to compute moment tensor in real cases?
Well, to calculate a moment tensor, you probably want an earthquake that is larger than 5.5 or magnitude 6. If you have enough local seismometers, you could probably do it for something smaller than that.
Okay.
Any other questions?
So can you model a single force using a moment tensor inversion?
Can I model what using a moment tensor inversion?
Single force, like centroid single force inversion. Like single force means that is used
I'm
to
not sure.
model landslides and all.
Oh, yeah, so volcanic blasts and landslides can be represented by a single force. That's true.
So there is one question in chat.
Sorry, can you say that again, please?
There is a question in chat box.
There is a question in the chat box.
Yeah, sorry, I didn't quite catch what you said.
Hey Derek, there is a question in the chat box.
Oh, okay. All right, if there are no questions, I will let you guys work on your homework.
Dr. Schutt, I think they were saying that there is a question in the chat box.
I think I just answered it.
Okay. Okay. Which one did you answer? The one from Indu?
Yeah, and then I also also answered how to calculate a correct SKS.
Okay. Okay.
Sir,
Yeah.
sir, regarding yesterday's homework, I think I had sent one screenshot in the WhatsApp group, sir. Actually, for the find channels, that code, whenever I'm typing SAC, nothing is the stack program is not running. I have shared the screenshot, sir.
How have you shared this screenshot?
Yeah, in the WhatsApp group, sir, that we have for this course.
Oh, I will look. So I'm guessing SAC is not in your path. Can you type which SAC and see if anything comes up?
Sir, actually, whenever I'm typing SAC on its own, so the SAC program is running. So, but whenever I'm doing this, putting this command there, so it's showing that bash it's doing something like it's not matching. Some bash is not matching, and another thing is that the program it doesn't run. So whenever I type Control D and try to get out of the get out of that, so it's showing that bash does not match. There is some error in that.
Well, I can see that you're trying to run find events and find channels in SAC, and you actually have to leave SAC to run those.
No, I have left SAC, sir. I am running this program out of SAC only, running this code.
Okay. So, and you get a bash error?
Sorry, sir.
And so I don't quite see what's going wrong here.
Yeah, so the thing is that once I write the first line of the code, then I'm going to this cd dot slash seismogram slash this thing. After that, whenever I'm trying SAC, ideally the SAC should be running, but there is nothing going on, and only this there is the no process is going on after I type SAC.
So that would suggest to me that SAC is not in your path. Can you type when after you CD into that event directory, can you type which SAC and tell me if you see anything?
Okay, I'll do it, sir. I'm just actually I have a dual boot system, so I'll just get back to my Linux system and then I'll just let you know, sir. Give me just
Okay.
5 minutes. I'll just let you know.
Sure.
Yes, sir.
Yes.
Sir, I have typed which SAC, so it's showing user local SAC bin then SAC.
Okay, so it's able to find SAC, okay, but it doesn't when you CD into a directory.
Yes, sir.
Um, hmm.
So, do you want me to share the screen?
Yeah, that would be great.
Just also, sir, another thing is that that program that code for SO which we downloaded from SOD. So I think there is some issue with the Java because in that manual for in the manual in the page from where the SOD was supposed to be downloaded, it said that the Java should be of a version 1.7 or higher. So I checked with the Java version which I have, and it is higher than 1.7. But still there are some issues with that find channels, that thing, find seismograms and find channels.
Okay, it may be finding an older version of Java on your machine.
No, actually, I installed the latest version after when I checked, it said that it should be 1.7 or higher. So mine is 1.8, sir.
Okay. I'm not sure what to do about that.
Yeah, sir, I'm sharing my screen right now. I'm
Okay.
actually, yeah, just a second. Sir, so this is the code find underscore events. So when I am pressing enter, so this is here, and so I have then typed this one cd dot slash seismogram slash events. Then I am typing SAC. So after I type SAC, nothing happens. SAC doesn't open.
Okay, can you type which SAC right there?
Okay. No.
All right, so my guess is that SAC is not in your path. So
So
what if
what
you
do I do,
try,
sir?
what if you try,
And when I'm exiting this, so this is showing unexpected EOF while looking for matching. Some single quote, something is there.
try typing the whole path to SAC that you got from the which SAC that worked.
Okay. So do I enter into it?
So you go type
Like,
user local SAC bin SAC. I think that's what it says there.
yeah. So this one is the for the SAC. The path is user slash user local slash local slash SAC. This one. So
Okay.
if I
Can you,
type this, yeah, I'm typing it right now.
okay.
Yeah, I have typed it, sir. So this
Okay, yeah.
is
So you can either change your path in your bash profile, or you can just type that whenever you need SAC.
No, but then how do I run this code? Find underscore events, this one, find events minus B2011, this one, this line, sir, this line.
Well, then you would quit out of sec and then run that line.
Yeah, so when I'm quitting out of stack, so this is here. So when I'm again trying to do this, the problem is I have quit out of SAC. Now I have typed this line, and then when I am doing this,
All right. Can you type which find events?
okay, do I get out of this, sir?
Just go back to the cursor.
Excuse me, you can remove greater than symbol before find events. I think that will create issue.
No, just a second.
Yeah.
Actually, even if I remove that, yeah. So so the problem still persists. Sir, kindly could you tell me again what to do?
So type the whole path to SAC that you got from the which SAC that worked.
Yes, this is the path, sir.
Yeah, then that seems to bring it up okay. And you might have to type the whole path to
Yeah.
find events as well.
So do I type which find events?
Yeah, you could, just because if that's not working as well, we could determine whether that's in your path. Okay, it isn't.
No, I think, yeah, it's not.
So
So
you need to go back to where you can access find events and then type which and see where it's located. And then type the whole path to find events, and as well as find channels and find seismograms. Or you can just put it in your bash
Sir,
profile.
just a second, sir. I'm going there. Yeah, so I have these lines here in the bin.
Okay. So you either need to type that whole path to find events, or you need to put find events, that location, in your bash profile.
Okay, so I'll just check the path. So this is the entire path.
Okay, that's interesting. I do see SAC in there. I don't see find events though. I don't see SOD.
Yeah.
So the simple solution is just type the entire path to find events every time you run it.
Okay, sir. Okay, I'll just try, sir, once. So I copy this one, and I think I can work in this directory only.
Okay.
No, can I work in this directory, or do I need to get out of this directory?
You probably need to get out of that directory because you probably don't have write privileges in it.
So I'll just clear the terminal once. That's better. Uh, so in this one, where do I put the path, sir? In this line?
Well, I can't really see what you're doing, but
Yeah, sorry.
okay. So you're going to need to put the path to find events, the path to find channels, and the path to find seismograms. Just because it's not showing up automatically. So you got to do user local sod,
Yeah.
whatever.
Yes. No, but where do I put that path? Where in this line?
So rather than find events, you need to type user local sod bin
Okay.
find events.
Okay. Okay.
And then you need to
Okay.
do the same thing for find channels and find seismograms.
Okay. So if I just remove the part after this pipe and just check whether it's working or not, can I just remove this part?
Yeah, that should generate a recipe.
No, no such file or directory.
Because you're not giving it the path to find events. You're giving it your general path.
Okay. Okay, so I'll just check, sir, once, and I'll get back. Sir. I'll just check it
Okay.
once myself.
All right, does anyone have any further questions? All right, I might take off now because it's my bedtime. And if you do have any questions, feel free to send me an email, or we can talk about it at our tutorial session. All right, I will see you all